Ever wondered how some AI can instantly categorize an email as spam, or suggest a movie you might like, all with surprising accuracy? Many of these simple yet effective decisions are powered by an elegant statistical concept known as naive Bayes. It's a foundational algorithm in machine learning that beautifully illustrates how probability can drive intelligent classification. At its heart, naive Bayes is a probabilistic classifier, meaning it predicts the probability of an item belonging to a particular class. Imagine you're trying to determine if a fruit is an apple. You might look at its color, shape, and size. Naive Bayes tackles this by calculating the probability of a fruit being an apple, given these observable characteristics. The entire framework of naive Bayes is built upon the pillars of probability theory. Specifically, it leverages conditional probability, the likelihood of an event occurring based on the occurrence of a previous event. It's the chance of a happening, given that B has already happened. Consider the probability of rain. If you wake up to dark clouds, the probability of rain increases significantly. This is conditional probability in action P. We're assessing the likelihood of rain, conditional on the observation of dark clouds. The hero behind naive Bayes is undoubtedly Bayes' theorem. Formally, it states P equals P asterisk P/P. In simpler terms, it helps us find the probability of a hypothesis given the evidence, by relating it to the probability of the evidence given the hypothesis, and the individual probabilities of the hypothesis and evidence. This theorem allows us to update our beliefs or probabilities about a hypothesis as we gather new evidence. Instead of guessing, we use observed data to refine our understanding, moving from an initial belief to a more informed one. This is crucial for making accurate classifications. Now let's talk about the naive part. Naive Bayes makes a powerful, simplifying assumption that all features used for classification are independent of each other. This means the presence or absence of one feature doesn't affect the presence or absence of any other feature, given the class. For example, if we're classifying an email as spam, naive Bayes assumes that the probability of seeing the word Viagra is independent of seeing the word free, given that the email is spam. While this assumption is often unrealistic in the real world, it dramatically simplifies the calculations. This independence assumption is what makes the algorithm computationally efficient and surprisingly effective. It allows naive Bayes to calculate the probability of an entire set of features given a class by simply multiplying the individual conditional probabilities of each feature. We then pick the class with the highest overall probability. Let's apply this. To classify an email as spam or not spam, naive Bayes looks at keywords. It calculates P using Bayes' theorem. It then compares this to P and assigns the email to the class with the higher probability, leveraging its naive independence of words. Despite its simplifying assumption, naive Bayes offers several compelling advantages. It's fast, efficient, and performs remarkably well even with relatively small datasets. It's particularly effective in text classification tasks, like spam detection, sentiment analysis, and document categorization. From recommending products to diagnosing medical conditions and filtering junk mail, naive Bayes continues to be a cornerstone in the world of machine learning. Its elegance lies in its simplicity, demonstrating how a robust understanding of probability can power intelligent systems with surprising efficiency and accuracy.